Is it working?
No.
It's not working?
Now I can listen.
No? Ah!
Yeah.
Now it's working.
Perfect. Okay. So we will continue with our last session of cosmology with neutrinos. Just a small message for the people that want a certificate that come to this workshop, or that they have to ask it directly to Katarina, because we are not going to do them by default. So you need to ask personally this if you need it. Thanks. You can start.
Is it working out? Yes. Okay, sorry. So what I said was that on Wednesday I discussed how to extract information about neutrino properties and neutrino-like particles from the CMB, and also I briefly mentioned BAO, so baryon acoustic oscillations in a single bound, but I didn't discuss what the experiments used to extract them. So I missed a few linear probes, because in fact this is the suppression in linear theory of the matter power spectrum due to a neutrino mass. So we see we have this suppression effect here. So there's an effect. There's also an effect due to lensing, which we can see in the EE power spectrum, and this is this is the sound horizon at decoupling divided by this volume distance as a function of redshift, and this is these BAOs, which you can measure at different redshifts with different experiments. And you see there's also here there's an effect on the neutrino mass. And here up here we have the convergence power spectrum, which is also something you can, all these things are something you can compute using a linear Einstein-Boltzmann code like class. And of course in this tail here, this is L, so that's the angular diameter the multipole, which roughly means that this is small scale physics. So for these, at these scales, this is no longer linear, but we see that most of this, and where we have the big effect, is at linear scales. So, looking at this convergence power spectrum is also a good way to measure neutrino masses. And what is nice with the linear physics is that it's very easy to make the calculation. You can make it in a second usually, and there are no difficulties in the calculation. But if we really want to maximize the information that we can extract from future surveys, we need to understand how neutrinos affect the nonlinear scales. So the idea is to measure the neutrino mass by looking at the clustering of galaxies and also galaxy lensing. And I just highlight one experiment, Euclid, which has a scheduled launch in 2021. But I just learned that there's a quite strong competitor, DESI, which is supposed to start data taking in 2019. So it will be interesting who will get a measurement first. But I think both measurements, I don't know what about DESI, but I looked up something quickly, and it seems also to be in the range of 0.2 eV sensitivity, as it is for Euclid. And 0.2 eV, I know, should it be 0.2? Yeah, okay. So we see that with this, we're supposed to be, even at the minimal, even in the normal hierarchy, for the minimal sum of neutrino masses, we're supposed to make a 3 sigma detection. But it's not, this is a forecast, so this is just some people who wrote it in a design study for the instrument at some point, but to actually achieve this, we need to understand the impact in the nonlinear regime. So we want to do the same thing, this cosmological inference thing where we vary parameters, we compute some observable, we compare the observable to data, and we go back. But now we want to do it, for instance, with the matter power spectrum. And we want to compare with something like this, which is a map of galaxies. So this is much more difficult because this is no longer governed by linear physics. So there are basically 2 problems you can say. So the fundamental problem is that we cannot solve the correct equation. The correct equation is the Boltzmann equation. So for the linear CMB, we are really solving the correct system, the Einstein-Boltzmann equation. And we would like to solve the same equation, but also in the nonlinear limit. But that's just impossible because numerically, because the Boltzmann equation is an equation for the distribution function. And the distribution function lives in a 6-dimensional phase space. So if we want to have any cosmologically interesting simulation, then it's simply impossible to solve the Boltzmann equation. So for cold dark matter, we have in principle the same problem, but because cold dark matter is very close, we can integrate out the momentum dependence and the distribution function very easily, and we just sample particles instead. So that gives rise to this n-body simulation. But of course, an n-body simulation is not solving the Einstein-Boltzmann equation; it's an approximation. So how can we understand this approximation in terms of the true system of equation, which is the Einstein-Boltzmann equation? So that's the first problem I will talk about. And the second one is how we can implement massive neutrinos in the n-body simulations in an effective way. So first is this Newtonian approximation that is implemented in n-body simulations. It's how we do an n-body simulation is by we take space-time and let space-time evolve with a scale factor a in the background, and then we just solve Newtonian equations on top of this expanding background. So the question is, can we go beyond this approximation? And to do this, we need to introduce a few concepts from general relativity. So depending on how much cosmology you've seen, here's a quick reminder. So in general relativity, we have a metric g mu nu. So it's a symmetric 4x4 tensor. So we have 10 degrees of freedom. And in linear perturbation theory, we usually write this system of equation. We write the metric tensor in this form, a general form, where we have a shift B here, and a lapse perturbation A, which affects the 0,0 component, and then we decompose the spatial part of the tensor in this way. So we are doing this scalar vector tensor decomposition, where we are separating each perturbation in terms of how it transforms under spatial rotations. So that is nice because at first order, all the physics, the Einstein-Boltzmann equation decomposes into scalar vector and tensor perturbations. We start with 10 degrees of freedom. If we then do this scalar vector tensor decomposition, they are split up in such a way that we have 4 scalars, 4 vector degrees of freedom and 2 tensor degrees of freedom. Now, because in general relativity we have diffeomorphism invariance, so the physics has to transform covariantly under these such a coordinate transformation where we are making an infinitesimal transformation of the of our coordinates. So because such a vector epsilon here can be also decomposed into two scalars and one divergence-free vector that has two degrees of freedom, this diffeomorphism invariance removes two scalars and two vector degrees of freedom. And then finally we have this form here. Then I know this is the general form, so we have not used the gauge conditions yet. And what is two common gauges to use is this Newtonian gauge and the synchronous gauge, which are specific ways of implementing this. We use this gauge invariance to kill this extra gauge freedom. So what you realize is that if you write your continuity equation and your Euler equation for the cold dark matter, it can be written in linear perturbation theory in a very simple way here. And now you can try to think, you can write down the general continuity equation and general Euler equation for the cold dark matter in a general gauge. And then you can see if you, by playing around with the gauge condition, if you can find a gauge where these two equations here are very close to this equation. And indeed this is possible, and it's called the n-body gauge. So we see that they are really almost exactly identical except for this small gradient gamma down here, which is like which you can show is only sourced by radiation terms. So in fact, these two equations can be realized in a one-parameter family of gauges, but only one of them will have the same relativistic energy density as you measure in the simulation. Because when you compute, when you want to solve the Poisson equation in the simulation, you count particles, and then you derive the energy density or inside the simulation from the particles. But that's a counting density. And in general relativity, there's also a possibility of having a volume deformation of space itself, and that changes the energy density. So there is a possibility of having this a volume deformation term HL, which is obviously never included in the simulation. So people are not including this volume deformation, which would be there in a large variety of gauges. But there is a specific gauge, which was this n-body gauge, where you can simultaneously get these nice equations here and put HL to 0. And then the only error you make is in the Euler equation for the cold dark matter, because you know that you are neglecting the term that comes from neutrinos and photons. So you can now try to estimate, or you can try to compute in linear theory this effect, the ratio of the gamma to the gravitational potential phi that comes from cold dark matter. And you find that at redshift about 49, this term is roughly 1%. So it seems that if you start your simulation late enough, you can neglect it to some position. But indeed, you can do even better, because we can use this gauge freedom in a more clever way. We can define the gauge in such a way that cold dark matter particles follow Newtonian equations inside the simulation. So it turns out that this is just a definition of the gauge, the Newtonian motion gauge. So it's illustrated here that if you have let's say we have an n-body simulation, the particle moves like this. In the Newtonian motion gauge, the particle is also supposed to move like this, because that's how the gauge is defined. This is how it would move if all general relativity was included, or if all radiation perturbations were included. Then it would do like this. But this effect can be can be taken care of by just having the coordinates move in the correct way. So that's what this Newtonian motion gauge does for you. And of course it only works because this is a very small effect in the end. So then if you take your unmodified n-body simulation, after you've run it, you can run an Einstein-Boltzmann code. You can compute some spatial gauge transform, and then you can in principle apply this into the simulation and move things correctly, so that you're in accordance with the general relativity. So now you might think that you're missing something because we are just adding the radiation directly into the simulation. We are not adding the radiation to the simulation, but we are just post-processing the output of the simulation. But you could try to add this. This is just a new force term, in fact, inside the simulation. So you can just try to add it inside the simulation as time goes by, and then you can see if you find the same result. And indeed, that is the case. So that is the relative power spectrum from including or not the radiation perturbations. And the dotted line is what you expect from a linear calculation using this Newtonian motion gauge approach, while the solid lines are a real n-body simulation where the radiation perturbations have been realized inside the simulation and has been taken into account when you compute the gravitational force. So now another problem is how to set initial condition for n-body simulation, and this is in fact related to this neglect of radiation perturbation. So there's a trick that's called backscaling. It might not be as well known outside of the community, but it's something that when you think about it, it's a little bit weird. So the way that an n-body simulation, the way you would normally think about using an n-body simulation to solve for the cold dark matter distribution would be to first you take some initial condition for inflation. Then you evolve that initial condition forwards in time using a linear Einstein-Boltzmann solver. Then at some point where you think that non-linearities become important, you take all this, the information you have, you copy it into an initial condition for the n-body simulation, and you let the n-body simulation evolve until today. So this is not how it's done in practice. Instead, an Einstein-Boltzmann code is used to compute the linear matter power spectrum today. Then it's this matter power spectrum is scaled back in time using a growth factor, and in fact it's scaled back using the linear Newtonian solution, and then it's solved forwards in time again using the nonlinear n-body simulation. So this is slightly confusing. Why would you do this? So it's done like this because this guarantees that on linear scales, what you put in from your Einstein-Boltzmann code here will be recovered by the n-body simulation at linear scales as long as the n-body solves equations that are also correct at linear order, which it should, of course. So now you can try to understand this backscaling approach in Newtonian motion gauge. So it's slightly complicated, and I will just show you a few equations. But the idea is that you want to match your boundary condition at the final time, and if you're an n-body gauge, you can solve this by there's a solution which sets this metric perturbation to 3 times this co-moving curvature perturbation, and once you have radiation perturbation, this becomes slightly more difficult, and I'm going to skip ahead because this becomes okay. So this is the most important plot. because this shows how metric perturbations in the n-body gauge and metric perturbations in the Newtonian motion backscaling gauge for different wave number of k converge upon each other. So after a certain time, using backscaling simulation, you are in fact in the n-body gauge where you don't have the radiation components. So what this tells you is that if you just do what people have been doing for a long time, using backscaling initial condition, you can more or less forget about radiation perturbation and assume that you are an n-body gauge in the simulation. So of course it's a bit, yes?
Can I ask a question?
Yes?
With the backscaling, you're saying that it's better because you ensure that the linear terms are preserved. But if you don't trust the system with n-body with the linear terms, why would you trust it with the non-linear that you don't really know how it should evolve?
Yeah, the n-body, yeah, so you really need to trust the n-body is doing the correct linear stuff. And indeed, it's the first test you should do if you write a code.
Can you go back a slide?
Just one? Or
No, the other one.
this one?
Here.
Yeah.
Yeah, the non-linear modes. Sorry. I mean, going back, you're putting back the linear and the non-linear modes, right? And you're saying that it's better than the first one because you ensure that the linear terms are correct at redshift 0.
Yes.
If the n-body doesn't give you the correct result to redshift 0 for the linear ones, how can you trust the non-linear ones that you don't really know what you're trying to get?
Yeah.
So if you don't trust the linear, you may not trust the non-linear whatever result you get.
Yeah. So what would go wrong here is that when you look at the final power spectrum at linear scales here, even though the n-body simulation is solving the correct linear Newtonian equations correctly here, because there are radiation contribution in the real system, and these are ignored in the n-body simulation, it's the power spectrum at the linear scales is in fact wrong in this approach. So you see you have a few percent error on the linear scales just because you don't have the radiation perturbations in n-body simulation. And this is what you can get using this this funny trick. Is that does that explain?
Well, yes and no. I mean, I understand it's a complicated thing and it's not easy, I mean, to do it, but since with the non-linear ones, you don't really know the answer. So you trust your software and it gives you the results and you trust it because it can keep a surprising thing. I mean, if you have an engagement in the linear power spectrum, in the non-linear you could have an extra engagement or a suppression. I mean, how it works.
Yeah, and exactly this was the reason that we were quite unhappy with this for exactly these reasons. That once you're doing nonlinear physics, I mean, what do you know in the end? So how we were understanding this in the beginning was that this thing here puts you in some fake universe that you don't trust. I mean, you're doing several mistakes somehow, and why should I expect these things to just work out? So the thing is that you can what we then did was to understand this whole procedure, but in a fully relativistic setting. And in that one, you can understand this procedure as just a way of setting initial condition for the Newtonian motion gauge. And then you can actually compute what's happening in this, and you see that it works. But I think before our paper, people were using it without knowing that it works. So they had, of course, a gut feeling, but I think the paper in this approach shows that it in fact it works. However, there's an interesting thing that I've not put in the slides, and that is that it works only in lambda CDM. So this thing of going back and going forth again is extremely sensitive to the physics. So, for instance, if you have decaying cold dark matter, you're creating radiation at late time. And this works by creating, there's a decaying mode that when you go backwards in time, it blows up. But because the radiation is only, the relic radiation is very subdominant in the beginning, at the final time, and it comes here. So it means that this decaying mode is kept under control and the initial condition is well defined at this point. But if the cold dark matter particle, for instance, or you have another source of radiation at late times, then this approach is completely wrong, because your decaying mode here will get a kick, and then when you are here, you're far in the non-perturbative regime, so you don't know how to set your initial condition for the in-body simulation, and then you don't know. So yeah.
Would that be the same for dynamical dark energy?
Yes, it could.
Not decaying into relativistic, just dynamical. So it's different than lambda code dynamics. Would that be?
If the only thing you do is to modify the Hubble constant, then you are fine in this approach. But once you start to have some non-trivial dark energy perturbations or something like that, then you could be in trouble. And then this thing here, and using Newtonian motion gauge is the safest approach.
And what percentage would you suggest if you have dark energy perturbations as sub-percent in the linear term, or what level would you say, well, you have to consider them or not? Do you have an indication of that?
I think if they happen to be strong at late times, which would be the usual case for dark energy perturbation, and if they are comparable to, if they are much stronger than the relic radiation perturbations, then I would be concerned. So, yeah, I'm not sure I can put a number, but maybe, no, I will not put a number on that. I would say that you should try to compute and see if there's a problem. You basically have to solve this equation then. Okay, and this is just a plot that shows this growing mode and decaying mode. So this is relevant because you need to use the correct, when you do this backscaling, you're computing a d factor, which is a solution to the growing mode equation. And this is the one you want to set your initial condition in the in-body simulation in this backscaling approach. And now it matters how you are solving the Friedmann equation in the simulation. So it might come as a surprise, but in many codes, radiation is not included in the background evolution of the Friedmann equation in the in-body simulation. And this means that at early times you don't have a direct correspondence between redshift in the simulation and redshifts in the real universe. So this is something that if you are not including it, then you need to make some sketchy translation. Then if you include radiation inside the Friedmann equation, there's a risk here, because the standard equation that people use to compute this growing mode growth factor D is no longer correct, and you need to solve the differential equation directly. And this is a non-negligible effect, so you can see that depending on what approximation you're using, and these approximations exist in codes that compute initial condition for in-body codes, also codes that are being used. So it's something that you should be aware of if you're doing this. But you see, we have percent effect difference in this growth factor if you're not doing it correctly. So what you have to do is, of course, to solve the real Newtonian growth equation to get the right result. And this is also very relevant if you have dark energy, because all these equations that are being used in the literature, they only correct for lambda CDM. So once you have just W0 being different from -1, then they break down. So, and then if you want to run your in-body simulation, you really need to compute the correct value of D. Okay, so now it's problem 2, which is something that I've only started working on recently, so you see there will not be so many slides here. But neutrinos, as long as neutrinos are massless, I just showed you how to include them, because we can include them in various ways. In fact, we can compute the full effect of the massless neutrinos just through post-processing, just by running an Einstein-Boltzmann code after the simulation. But if neutrinos are massive particles, they will at some point start to cluster, and that's a non-trivial effect and a nonlinear effect that we have to include inside the simulation. But this is not so easy, because neutrinos have very large thermal velocities, so which generates a noise term in the simulation. So okay, so there are various approaches. So the first thing, the easy thing, is to at least use a correct initial condition for the n-body simulation. So it means that we should take, okay, it sounds almost trivial, but it's also something that might not always be done. So you need to take the power spectrum that includes, the linear power spectrum that includes massive neutrinos. And you need to start your, you need to initialize your cold dark matter using this power spectrum. This is not so trivial, because now also this backscaling doesn't work anymore, because this d factor would be scale dependent, and yeah, so it's a bit tricky. But at least putting the right initial condition for the cold dark matter is step one. Then the next thing you can do is to actually put in the particles, put in neutrino particles in the simulation. So remember, I said we need to solve the Vlasov equation. So this is an approximation. So what you do is that at every time, at every position in space, you're putting in several particles, each sampled from the Fermi-Dirac distribution. So it means that you have some particle ensemble that in total describes your distribution function. And then you just hit the button and you solve this in the n-body simulation. So it's extremely easy to implement in existing codes, but it's also very difficult, especially now that the bound on the neutrino mass is so low, because it means that these particles are relativistic for most of the lifetime of the simulation, and they start to, or maybe they are not relativistic, but they have large thermal velocity for a long time in the simulation. And this creates a noise term, and this means that when you do that, you realize that most of the time you're just simulating white noise. And it's not very bad, because in fact one of the main effects that neutrinos have on cold dark matter is through a white noise term. It's because the noise term is destroying structure on small scales and makes it more diffuse. So it's not all wrong, but it's just, if you look at the neutrinos themselves, you can see that this is not neutrinos that cluster. This is just the noise you have in your simulation. But this is, so this was pioneered by Brandbühl et al. And this is what is being used in many codes, simply because it's very easy to implement. Because the only thing you need is to duplicate your cold dark matter. You just need another species which you put some other initial condition for, and then you run. Another thing you could do is you could solve the linear equation side by side with the n-body simulation, and then you feed the information from the linear calculation into the n-body simulation. And that's something that you expect to work well for very small mass particles, because then the evolution equation for the neutrinos are approximately linear through the whole universe. Then the final one, also pioneered by Brandbühl and Hannested, was the hybrid approach. So in that one, you will evolve the particles, the neutrino particles, on the grid until some redshift, and at that redshift you dump most of them as particles in the simulation. So this has this nice feature that the large thermal velocities that was a problem if you start initially with the particles. If you are able to dump them at, let's say, redshift of 6, then these thermal velocities have been damped a lot, and you don't have too strong noise term in the simulation. But now, okay, and this is then the relative suppression of the total matter power spectrum. So 0 is what we would get if the mass of neutrinos had no effect. The solid line here is what you expect from linear theory. So you see lots of this suppression can indeed be understood just in linear theory. But if you want to go of scales much larger than 0.3, the nonlinear effect becomes important, and we get this spoon shape here that is very characteristic for these massive neutrinos. And this is computed using this hybrid approach, in fact. But we are now working hard on a different method, because many of the approximations in this hybrid approach are a bit difficult to test, and also it's very difficult to have such a code that it's very hard to take some of the distribution function and dump correctly on the grid. So indeed, the code exists, but we want to have something better. And this is this new concept, which is based on a code called concept, which is written in Python, in fact. This is like a test code where once we have a scheme that works reliable, the idea is to take this implementation and translate it into a production code like Ramses. So what we do here is, of course, the particles, the cold dark matter particles are just n-body particles, so that's fine. But the neutrinos are then solved using a truncated nonlinear Boltzmann equation. So yeah, and okay, so we are just about finishing the release paper here. I've been courageous and put 11 here because I think we will be putting the paper out later this month. So first, you can take the n-dimensional tensor can be expressed in terms of the distribution function in this way, and now you can generalize it, and you can take the third cumulant of the distribution function defined in this way. So we see we have now no momenta here in the numerator, and then okay, so you do this. You take your Boltzmann equation and you find evolution equation for these moments. So when you translate that into fluid variables, you find a very complicated expression for the density contrast. I just want to impress you with the sheer size of this equation, and also a very non-trivial Euler equation here. So all this is, I even showed you in linear theory the corresponding ones for cold dark matter, and they are extremely compact. But once you have pressure term inside your species, you have to deal with, and also you have general relativity here. But you have this W equation of state parameter showing up, and you have pressure perturbation that is not given in terms of the energy density perturbation. So now these equations cannot just be passed into the code, because to have a stable evolution, we need to have all the equation in this flux conserving form. So we define some effective energy density in this way, A to 3 1 plus W, and if you remember correctly, if W is constant, then this one is exactly constant in time in the background. But that equation still holds if we just define W in terms of, even for a time-dependent W, you can define a W such that this equation holds. And this is what we do. We have what would it be called? A current J here, and we have some pressure here that is written in the same way as up here. Okay. Now, in this flux conserving form, we have a much simpler system of equation here. Not much simpler, okay, much simpler is maybe an overstatement. But of course, as you can imagine, we are truncating the Boltzmann equation, but how do we do it? So every time you truncate an equation, you make an error. And one way to make a truncation is just to put higher order momentum to zero. So from a physical point of view, we expect higher cumulants or higher orders to be suppressed simply because they get more physical momentum divided by energy in the integral, and the energy becomes dominated by the rest mass of the neutrino. So at late time, we expect these higher order cumulants to be suppressed and have smaller impact on the first moments. But if we just cut it, we could just put higher order cumulant to zero in our equation, but that would introduce a mistake, because then we would not even be solving the correct linear equation, and this is something we want to do. So instead, we close the hierarchy using class, a linear Einstein-Boltzmann code that computes the linear prediction. So then at least, okay, we are not putting in the correct thing, but we are putting in the correct thing to linear order. So we are sure that new concept will solve the correct equations in the linear regime. So there are two things that we need to close the hierarchy at this order. So that's the pressure perturbation and the anisotropic stress perturbation. And we get them in this way: inverse Fourier transform of the nonlinear energy density perturbation in Fourier space multiplied by the ratio between a pressure perturbation and a energy density perturbation from class. And this is also an effective sound speed, in fact. And we do the same thing with the anisotropic stress tensor. One might think that it would be, because you can also imagine that I just realized using the same random numbers that I used to set up the initial condition for the n-body simulation, I could just generate these two guys by doing inverse Fourier transform using the same random numbers as I used to set up the initial condition for the simulation. And that's correct to linear order, but in nonlinear order this becomes very wrong. And that's because in nonlinear order the velocities are such that particles move in the simulation a finite distance, which cannot be ignored. So this pressure perturbation and anisotropic stress perturbation would in some sense be put in the wrong place inside the simulation, while if we do it in this way, it will be correct. And now it's just to show you, these are very fresh from the cluster. I just got the figures yesterday, and this is now at starting redshift of 0.02. This is a concept, and this is a class. So you see there's some difference initially, and this is okay. This is not exactly the starting redshift; it's slightly after the starting redshift, and this is due to pressure waves inside the simulation, because we are solving fluid equation, and they support pressure waves. So even if we are doing our best to put in the correct linear evolution, which would not have these pressure perturbations, we cannot remove them completely. But they are soon, because we have a strong forcing component from the cold dark matter, they are soon killed off. And now, moving forward in time, we see how nonlinearity starts to grow, and of course I haven't even said what is on the y-axis, because I'm not showing the total matter power spectrum, because we want to do better than just having a total matter power spectrum to 1%. We really want to have the correct evolution equation also for the neutrinos themselves. So this is the power spectrum of neutrinos in the simulation. So we see how the neutrino starts to cluster here on the small scales, and now everything changes, but that's because we have the hybrid approach is dumping its particles here at A of 0.4. This thing here, which is of course something that you see immediately. What is that? So that is the noise term that I was telling you about. So we see this is really, if you look at the scale here, this is white noise. So we cannot trust the hybrid method here. Here we see that it was realized the particles are dumped in accordance with the linear evolution from class. And you see already here, there's a slight problem because we are not putting the correct initial condition in the hybrid code, because the hybrid code initializes from a linear theory. But concept tells us that indeed in this area here, we are already seeing nonlinear effect. But as time goes by, the hybrid approach catches up because it has to catch up a bit in this regime here with the cold dark matter potential. But then, as time goes on, and this is indeed a redshift 1. So we see we have quite a good agreement with between concept and the hybrid approach in the regime where we can trust the hybrid approach. And up here we see we just become dominated by the sampling noise of the neutrino particles. Of course, it's very hard to judge who's doing the better job here, but you should keep in mind that this is even if it's a log scale, it's a very small error we have here. And if I just say that the error is estimated as the difference between these two curves, then this translates into a very small error in the total matter power spectrum, because the neutrinos themselves have a very small impact. They're only 1% of the budget, more or less. So in the total matter power spectrum, we see only a small effect. So yeah, the conclusions is that we believe we have a very good method for including massive neutrinos in the simulation, and I also claim that we understand exactly how to include radiation perturbations in the simulation. So I just want to say thank you for a very nice stay here in Mexico City. It was really been wonderful to be here and a nice workshop. So thank you.
Bueno, tenemos tiempo para unas cuantas preguntas.
Or in English?
Tenemos tiempo para mucho. In English. We have time for some questions. Please, the first one.
So when you told about the initial condition to be included as the massive neutrino, how is the, because in the radiation perturbation I can understand with the Boltzmann, but in case of the massive neutrino, how you input the initial conditions?
Yes. What we do in concept is to take the initial condition from class at the starting redshift, so without doing backscaling. And that's because we know how to include. The only reason to use backscaling is in fact just a cheap way of having the radiation effect. And now that we know how to include the radiation effect, then we just pass the information from class at the initial redshift, and then we solve forwards in time. And then what we haven't shown, but we know that it's true, is that we have the correct matter power spectrum at large scales. So this is something we probably should show in the paper, but I believe it's true.
In case of the massive neutrino, this neutrino will evolve to like a dark matter, right?
Yes.
It will be no more radiation evolution.
Yeah, indeed. So I think we really need to have the neutrino inside the simulation. There's no way around that if we want to have precision measurements. So maybe you're referring to the first slide where I showed that the first idea was to just having an initial condition, and for me that's just the first thing you must do. But of course, it's not enough. I think that's clear. It's we need the neutrino in the simulation.
But when you consider it's massive, it still have a pressure, right? Or it
Yeah, it has a pressure.
Okay.
Yeah.
So it is not exactly like a cold dark matter, because cold dark matter we don't have a pressure.
Exactly. Yeah. So that's why. Yeah.
It is like a transition. It has like from radiation relativistic to little bit non-relativistic at the later time as it's become massive.
Yeah. It makes a full transition from a pressure full fluid, and then goes down to having almost no pressure towards the end. Also depending on scale. Yeah.
So the initial condition you put is like radiations in even in the massive neutrino.
Yes. Okay. So that's a good question. We take a. Can I go? Oh, maybe this is fine. Yeah. We compute the density and velocity directly from class at linear order, and these are fluids. So it is really the correct initial condition for the fluid. In the case of dumping particles, then you do this thing about you sample from the thermodynamic distribution at each point. You just put particles within some region which are sampled from the thermodynamic distribution. In that case, you're not doing an exactly correct thing, because, for instance, your shear perturbation will not match the relativistic one. You have pressure, because the pressure comes from the thermal movement of the particles, but it's not a fully relativistic treatment. So it's also one of the weak things about the hybrid approach, is that it's not a fully relativistic thing. You're dumping particles. They have some pressure, but it's not a consistent solution, basically.
And do you need to provide for the normal n-body simulation, we have to provide initial condition for Jaldovics or Sino-Jaldovics like positions and like this. For the neutrino, you have to provide that also, or no? No need to.
No, we don't need it, because it's not a Lagrangian. In new concept, we don't need it because it's not a Lagrangian code. So that means that it's even easier to get it, because we can just directly take the output of a class and inverse Fourier transform it, and then we just get the field automatically. We need to have in mind what random numbers we used when we set initial condition, because we need to use the same random field all the time. Also the one that we use to generate Seldovitz approximation for the cold dark matter particles. Of course, in the hybrid approach, one has to use something like Seldovitz approximation or something to set to put the particles in the simulation. Yeah.
So the effect of the neutrino is incorporated in the cold dark n-body simulation. It's that.
In concept, there are both standard cold dark matter particles, and then there are fields that are being solved simultaneously in time. Yeah.
Someone else have a question?
So what is the effect of the energy distribution of neutrinos in the spectrum?
Yes. Yeah, so of course, if you have a non-standard distribution function, then the moments would, because of the momentum weighting, it would be different. So it's something that, yes. Okay, so this is something that could be computed now, because of course class can handle any distribution function you give, and it would give the correct initial condition based on this distribution function, and will also give the correct linear difference between for the anisotropic stress term. So you could see if there was any effect. I guess that to the accuracy of the code, you probably need a very sophisticated non-standard distribution function to get an effect. But it's something that you could do in principle. If you have any idea, it would be interesting. Yeah.
Any other question? No? If not, we pass to the next speaker. Well, thanks again, Thomas. So now we have Mark Chen that is going to give us our last session, neutrino masses and double beta decay in Star Plus. Just a reminder again, if you need a certificate, you need to contact Catalina to ask for it. We are not providing by default.
It's okay. Good. Okay. All right, so let me just recap where I left off from the first lecture. So in the first lecture, I talked about physics and the importance of searching for neutrinoless double beta decay as a way to explore neutrino mass and understand the character of the neutrino. And experimentally, the way to look for the neutrinoless double beta decay is to search for events at the end point of the ordinary double beta decay in which two neutrinos are emitted. And so then I mentioned that the challenge then is that the rate of the neutrinos double beta decay is very small or even could be zero, and so we're trying to find evidence for this process amidst potentially the more dominant signal of the standard model allowed to neutrino double beta decay. So it's looking for these events at the endpoint that will characterize the experimental search, and then at the end of the first lecture, I quickly described the desirable characteristics are to have a large signal, have a small background, and to ideally have some identification characteristics in the experimental technique for identifying the neutrinoless double beta decay. And I concluded with a couple of words about the isotope choice, which impacts trying to get enough signal, and then some words about background. So today's talk, I want to go through and talk about some of the neutrinoless double beta decay experiments that are currently running or soon will be running. And in doing this survey of the different experiments, then I have to make 2 points to begin with. One is I have to make apologies that there's no time to discuss all of the possible all of the experiments that are there. So I'm only going to speak about a few of them as a way to illustrate the techniques that are being pursued by these different experiments. And then the second point I make is thanks to all of the people whose slides I have borrowed from for presenting the other experiments. So there are 3 classes of the experiments that I'll talk about, representing 3 approaches for trying to see these neutrinoless double beta decay events. So one class of experiments are essentially calorimeters that have excellent energy resolution by trying to really find a peak at the endpoint, and those include germanium detectors and cryogenic bolometers. In contrast, another class of experiments are loaded liquid scintillator. So those experiments, they feature the possibility that with a large liquid scintillator, you could potentially deploy a lot of the double beta decaying isotope in the liquid scintillator and then achieve the very low backgrounds that you can achieve in a liquid scintillator, as we heard from Andrea, like Borxino did. And then two experimental approaches are Camelot Zen, which puts xenon in liquid scintillator, and Snow Plus, which puts tellurium in liquid scintillator. So in contrast to the above, the energy resolution is not good in a liquid scintillator compared to germanium detectors or bolometer, but then we'll examine this at the very end when I talk about Snow Plus. And then there's one more category, are detectors that have some tracking information, and I include EXO in this category as well, in which by seeing the tracks, ideally you can see that 2 beta particles were emitted in the event that then provide some ability to identify that the decay was a double beta decay. And so I'll try not to spend too much time on each of these experiments. There's really way too much material. I already have too much material to present. And so for each experiment, I'm going to try to give you my comments about what are the special things that those experiments have done, and try to illustrate with some slides of some of the very special things that those experiments have done in order to be able to achieve these experimental sensitivities that are really quite remarkable. So starting with the germanium detectors, perhaps one of the more classic experimental approaches for neutrinos double beta decay search. The germanium detector, as you may already know, is used in gamma ray spectroscopy with very high resolution, and so the fact that germanium-76 is a double beta decaying isotope is then very convenient. If you enrich germanium to collect germanium-76 and then make that into a germanium semiconductor diode detector, then you have in your detector itself the double beta decaying isotope with very good energy resolution. So key for these experiments is that energy resolution is good in germanium, and that the experiments use very clever ideas and approaches to control the backgrounds. So there are 2 big projects currently. There's a third one in China as well. But the 2 big projects with germanium are Majorana in the US. And the statement here is that they use a traditional configuration in which there's a copper cryostat, and they use a shielding of copper and lead in a very sort of traditional design, but the challenge is to make very, very clean materials for the detector and for the shielding in order to reach the sensitivity they want. And then a very nice idea that was developed for more than 10 years by Gerda experiment, which is in Gran Sasso, which is to take the naked crystals of germanium and immerse those directly into liquid argon. And that provides the cooling for those crystals to operate the germanium detector. At the same time, you have the potential, and Gerda then successfully used this in their phase 2, to use the surrounding liquid argon as an anti-Compton veto, in which backgrounds would that could scatter, gammas that could scatter in the liquid argon would produce scintillation in the liquid argon that you could detect, and you would know that that's not the result of a double beta decay happening inside the germanium crystal. So those 2 projects, and I'll just illustrate a couple of neat things about them. For example, in Majorana, this notion that you have to really carefully control the background, they go to the extent that they are electroforming copper that is used in the detector in the cryostats. They're electroforming that underground. Because if the copper is on the surface, copper is a typical material used in low background experiments, because the contamination of uranium and thorium and then those sorts of radioactive impurities is small in copper. But then if the copper is on the surface, it can be activated by cosmic rays, and then the cosmogenic radioactivity then can become significant once we push the sensitivity of these next generation double beta decay experiments down. So then you have to resort to, if you want to use copper nearby your germanium crystals, you have to resort to making your copper, purifying it in some sense underground, and then electroforming copper. So here's the bath. You can see the blue color of this solution, and then you electroform, deposit the copper on this very pure stainless steel mandrel, and then you can collect that copper, and you use that for the cryostat, and you also, it's a very clean machine shop underground in the in the South Dakota Underground Lab in the U.S. And so that's quite remarkable, the work that they did in Majorana. But I'll focus my discussion now on the Gerda experiment, which has recently updated their results and have very good results. So Gerda experiment has an array of germanium detectors, so something like 35 kilograms of germanium detectors that are suspended right inside a liquid argon. And then this liquid argon cryostat lives within a water tank. So that photo that was on the previous slide is just the outside water tank. And that water provides shielding from gamma rays from background. And the water tank is also used as a muon veto with PMTs. But the key thing for Gerda is that the liquid argon is also read out by PMTs that look for the scintillation light of the liquid argon in order to use that as an anti-Compton veto. But then they have these crystals that are operated within the liquid argon. The production of these crystals, there are two types of germanium crystals, the standard coaxial and what they call these BGs, or also known as PPCs, P-type point contact germanium. So this is a photo, not from Gerda, actually but from Majorana, just to show you that one of these germanium crystals are typically that size, and then there's a point contact, which is a P plus doped contact, and then you have this N plus doped here, and then the intrinsic germanium, high purity germanium inside. But having this point contact, the geometry is odd compared to the standard germanium detectors in that now you have varying drift times depending on where the where energy was deposited inside the crystal. Whereas in the coaxial geometry, where one of the electrodes is in the middle and then surrounding the outside, then the drift time is just sort of radial, so fairly uniform. But here it's deliberately designed, the P-type gives you very low noise, but it's deliberately designed this way because then if you look at different types of events, this stands for single site events or multi-site events. So if you have gammas that interact multiply inside the crystal, then the different, and this is time on these axes, and this is some arbitrary units of either charge or current, then the different shapes that you pick up when you collect the charge and you measure the induced current flowing can give you some handle to separate these events. So if you have a double beta decay event, it takes place at a single site, so the events would look more like this, but if you see this sort of structure when you read out the current and charge, you know that comes from a background gamma ray that then maybe has Compton scattered in several places inside the detector. And you have some ability to reject surface backgrounds as well. So very nice to have that capability. And I'll jump to the summary slide for these germanium detectors. And as presented at the TALP conference in Sudbury this summer in 2017, these are the results from Gerda, which are very, very good results that in this search for double beta decay, they find, now I actually have to remind you, so to tell you what it is that we're looking here. So that's the picture, right? We're trying to find this peak at the endpoint, and this is what germanium detectors used to look like, where the Heidelberg-Moscow experiment even saw a peak approximately at the endpoint at 2039 keV, as well as other peaks, as well as other backgrounds. But what we're looking at here is now zooming in on the endpoint region. So zooming in on the endpoint region, and in comparison to the Heidelberg-Moscow experiment, then the Gerda experiment sees this. So then all the 2 neutrino double beta decay is off to the left at lower energies. And if you look at this region and their phase 1 data set and then their phase 2, where they also does a divide between the coaxial and the BG detectors, they have all of the events are all of the counts here that you see. And then after you put in the liquid argon veto, then you're only left with the events that have the darker gray that are filled in. And then after you include all the cuts, that especially is the case for the BGs, where you can try to cut the multi-site events, then you're really left with hardly any counts at all. And this is where you look for a possible peak for zero neutrino delta beta decay, and they don't see anything. In fact, they're background free for this duration of the data they collected. So they see no background or signal, and therefore they can set a lower limit on the half-life, right? Meaning that the half-life for the neutrino delta beta decay has to be longer than this quantity here. And this is these background index. This is a unit that gets used in the community, talking about how many background counts per KeV per kilogram per year. And so these are the sorts of numbers that they reach. So as an indicator for the amount of backgrounds within the region of interest around the endpoint for the neutrino delta beta decay. So Majorana experiment also has achieved very impressive background index as well. So then combination of those results from Gerda phase 1 and phase 2 then sets limits on the search for neutrino delta beta decay. And then I'll try to summarize all the limits on a plot later in this talk. So the future for germanium detectors as an approach for searching for delta beta decay is that the Gerda and Majorana collaborations are merging now, and they are calling the next project Legend. Legend is this large enriched germanium experiment for neutrinoless delta beta decay is the Legend, and they'll take the Majorana germanium detectors, around 30 kilograms or so, or maybe it's more than that. They have 30 kilograms of enriched, and then combine it with the Gerda crystals and enrich more germanium to get up to 200 kilograms or 250 kilograms of enriched germanium, which can still fit inside the Gerda tank and the Gerda liquid argon cryostat. So by combining those two crystals and the two collaborations, also trying to use some of these low background components that the Majorana experiment has developed, they have to push the background goals to be 5 times smaller. So 5 times smaller than what they currently achieved, and then they hope that that'll help them push the sensitivity for germanium down, with the ultimate goal to do 1 ton, 1,000 kilograms of enriched germanium, which is very, very expensive to enrich germanium, but that would be the goal, and that would be off in the future. All right, so similar to the impressive energy resolution you can achieve in a germanium detector is you can make a bolometer operated at cryogenic temperatures and use that to search for delta beta decay. So this program has been in existence for a long time, started by Ettore Fiorini. Ettore Fiorini? Yeah. In Milano. And starting from this small amounts of tellurium oxide crystals, and then building something that they call Core Chino and Core Zero, but the full-size project is this Core. It has 700 kilograms of tellurium oxide crystals, of which 200 kilograms of tellurium-130 isotope is present. And so you'll recall, I mentioned earlier too, that tellurium is an interesting choice for a double beta decay material because the natural abundance of the double beta decaying isotope is very high, 34%. So you don't have to isotopically enrich the tellurium. So with the bolometer, you also have exquisite energy resolution, and then this experiment also had very careful control of backgrounds, or attempting to do very careful things. What is a bolometer? So a bolometer is, bolometers, next slide. So then you take these crystals and you have to put it inside a cryogenic dilution refrigerator and cool it down to millikelvin temperatures. And then, one more slide. Okay, I'll jump to this just to explain what is a bolometer to people who aren't familiar. So when you cool a crystal down to those temperatures, then the temperature rise when you deposit a small amount of energy is a very significant signal. So what you do with these crystals is you attach a thermistor. These are neutron transmutation doped germanium thermistors that are attached to this crystal. So then if there's energy deposited by particles or radiation in the crystal, it heats up the crystal, and you can detect that heat as a pulse. And the pulses is a very clean measurement of the amount of energy that was deposited, because all the energy that was deposited becomes heat in the crystal, and you measure that temperature pulse. And so you can see here that the time scale for these temperature pulses is seconds. So these are very slow pulses, but provide an incredible measurement of the energy that was deposited with very high resolution. You can picture that arising because there are many phonons that are produced, thereby allowing one to acquire a very precise measurement of the quantity of phonons in this type of arrangement. So each one of these would be a cube of tellurium oxide, which is a crystal that this Milano group developed, that they found that if you cool to cryogenic temperatures can be operated as a bolometer with very high energy resolution. And because you have tellurium in it, then it becomes the medium for searching for neutrinoless double beta decay. So then they take these crystals and they assemble all of these crystals like this, and very impressive photos with these this apparatus where you're installing these crystals inside this very, very clean environment. And the assembly then also is done very clean because you have to glue these little NTD germanium thermistors onto the crystals, and then attach wires to the crystals, and then they're mounted on these copper structures that also provide some of the heat that is flowing in these. And so then overall core is this, then some 750 kilograms of these crystals, all in this big array. They're inside one giant dilution refrigerator, and this core experiment is in Grand Sasso. Contains about 200 kilograms of the isotope, and then what else do I want to say? It's been taking data since May of 2017, taking physics data since May 2017. So all of these crystals are cold, and they've required a couple of data sets now, and they also reported their first results at the TAP conference in Sudbury this summer. So what are these spectra here? So this is now the energy that's a spectrum measured by the crystals. And so then some of these events that you're seeing here are the 2 neutrino double beta decay. Okay, the stuff that's not as interesting. And right at the end point for tellurium, which is 2.53 MeV, 253, around here, then you zoom in and you look at the counts here now on a linear scale instead of a log scale. So you see these are the number of events that they see in the region of interest for searching for the neutrinoless double beta decay. Nearby, where you expect to see where one would be searching for the tellurium double beta decay, is a peak that comes from cobalt-60. Cobalt-60 has 2 gamma rays that then sum their energy to about 2.5 MeV, or 2.50 to be more precise. And the cobalt-60 comes about from cobalt contamination, but very trace levels of contamination in the components of the cryostat and dilution refrigerator. And there's some possibility there's some cobalt in the crystals themselves, but the Core collaboration sets a limit. So these are likely external gammas then have deposited energy, and that energy is very close to the endpoint. However, you can see that this is what the energy resolution is like for the cobalt-60 peak. So then the Q value, the double beta, is neutrinoless double beta, they would produce a peak here if it were present. And the best fit, when they do the analysis, has this negative peak. Right? So their best fit is a rate, which is negative, translates to a lower limit for the half-life. So they don't see neutrinoless double beta decay. In fact, they see less events than this background, flat background here. It means the background fluctuated low. So instead of reporting that they got lucky, so they, from this one data set, they have a lower limit, that's this. But then the median sensitivity for 90% confidence level background determined half-life for searching for the neutrinoless double beta decay is this quantity here. Okay, so then they're just starting their measurements, and then Core, though it does have a large mass of tellurium-130, and they've done a very good job over their program, starting from Core Chino and Core 0, coming down to this level for the background counts per kV per kilogram year near the region of interest. This is about a factor of 10 more than what was shown in Gerda. And so it is the case that the Quarry experiment does have some backgrounds here. And those backgrounds come from surface alphas. That if there's alpha decaying isotopes like polonium-210 that are either on the surface of the crystals or on surfaces adjacent to the crystals, those alphas then can make it into the crystal, and then they deposit energy there, which is just a heat signal. So trying to find a way to discriminate between alphas and betas or double betas is a little harder in this, although there are some cuts that the Quarry experiment uses, some pulse-shaped cuts that tries to do some surface background rejection. They do have anti-coincidence between the detectors, so if a gamma ray hits multiple crystals and lights them up at the same time, you know that's not a double beta decay event. So they do have some background rejection. And I mentioned that here because background rejection is an important part of these next generation double beta experiments, right? You need this big signal, or potential for big signals, small backgrounds, and background rejection techniques that are key. So the future for the Quarry experiment, so for each of these experimental techniques, also talk about what's the future incarnation, what are the experimenters planning. Here's a study from Quarry of backgrounds, and these are measured backgrounds, which are the data points, and these bars represent limits for what they think the background should be less than, and in these units of counts per kV per kilogram year. And it's the surface backgrounds, surface alphas, that are really the limiting background for Quarry, that make the deposit energy that then gives heat pulses that are sprinkled as basically a continuum across the spectrum, and so then therefore there'll be a finite number of counts in the window that you're going to look for, try to look for the neutrinoless double beta decay. So the approach of this Quarry collaboration is trying to take for the future efforts is an acronym called CUPID. And so CUPID is the Quarry upgrade with particle ID. And there the idea is if the surface backgrounds really are the limiting, you have to try to find some way to discriminate surface from bulk. And some of the ideas include that you can use Cherenkov light. So using the same crystals, the thorium oxide crystals, they don't produce any scintillation light, those crystals, but if there's a beta depositing energy in a crystal, it could produce a small amount of Cherenkov light, and you can try to detect that light, and you would know that's coming from beta in the crystal, not from a surface alpha, which makes no Cherenkov light. Or they're thinking about swapping the crystals, and then you could use selenium crystals as zinc selenide as a scintillating crystal, or the zinc molybdate is a scintillating crystal, and then both selenium and molybdenum have double beta decaying candidate isotopes. So then swapping to a different crystal, then you could use the fact that these crystals themselves scintillate, so then you can look for the scintillation produced by the alphas and from the betas, and use that together while operating them as a bolometer to achieve the high resolution in order to try to reject these backgrounds. Okay, so then that covers those experiments, or at least those are the examples of the experiments that are calorimeters with very high energy resolution. Okay, so another approach are experiments that have some tracking capability, and so I'll mention the EXO experiment, and then Andrea Pocar is lead PI in this experiment. So if you have any questions about EXO, then I'll eventually turn them over to Andrea. So, but my commentary is always here in the purple text with the square brackets. So xenon is a really good choice for a double beta decaying isotope because it's probably the easiest and cheapest isotope to enrich, to isotopically enrich. And so xenon, the abundance is something like 9%, xenon-136, natural abundance. But then because it's a gas, you can use centrifugation to enrich the xenon-136 to 90% or more or thereabouts to collect the xenon-136 to put inside your detector. And then also xenon, particle physicists, we know how to make detectors of the xenon. And so you can make a TPC from xenon, and liquid xenon would be the approach that EXO uses. And then you do have, with a TPC, you have the ability to have event topology to reject things like multi-site background from gammas. Not necessarily seeing 2 electron tracks in liquid xenon, because the electron tracks are very short in liquid xenon. But then the event topology is a very powerful tool, and the liquid xenon detectors that have good energy resolution, they have good self-shielding, because xenon's has a high atomic number, so external backgrounds kind of gets shielded by the xenon itself. And then there's this interesting possibility to try to tag the daughter isotope, the daughter nucleus, after the xenon decays, double beta decays, it makes a barium nucleus. And so the EXO experiment has been exploring this possibility as well. And let me start showing you some of the nice things that EXO has done. So EXO is currently EXO 200 has about 200 kilograms of xenon, approximately, enriched xenon. And it's in the WIP, Waste Isolation Pilot Plant underground facility in New Mexico in the US. And so in this facility, you can't see these pictures because they're dark. But in their facility, they have built an exquisite low background TPC. So what is a TPC? A TPC is a time projection chamber, a type of particle detector. And the idea in the TPC is that you'll have, say, this central cathode, and you'll have anodes at both ends. And then this is filled with a gas or a liquid, like liquid argon or liquid xenon. Then if there's a particle that makes a track, here the track is very long, then the particles that are making a track will ionize electrons from the xenon. Okay, so then you have a double beta decay and there's 2 electrons are emitted. But those electrons themselves will produce more ionization electrons as those electrons travel through the liquid xenon, in the case of EXO. And so then the electric field established by having a cathode and anode drifts those ionization electrons to the ends, and then you collect them with some way to read out the charge. And this then provides you ability to image the shape of the track and measure the energy deposit along each unit length of track. The xenon scintillates. So in addition to producing ionization electrons, you're also exciting xenon atoms and dimers that then give off scintillation light. And the scintillation light could be collected by, in the case of EXO 200, avalanche photodiodes that then measure the amount of energy. So you're getting a measurement of energy from the scintillation light as well as collecting the energy from the ionization that drifts to this anode plane that's collecting the charge. And so you kind of sum those up to get the total energy of the event that's here, as well as recording in 3 dimensions the position and shape of this energy deposition. So you get the position in X and Y from the charge collection on the charge collection plane by reading that out in a very standard way, and that high energy physics experiments do. And you get the Z position from the time that it takes to drift the charge. All right, so then EXO has built this TPC, and with Andrea's hands on all of these very sensitive parts of this TPC, and out of copper, low background, fairly thin vessel of copper, and then it's inside lots of shielding, and then installed in the underground lab at WIP. And so here's a photo of that copper cryostat being inserted into the shielding. And so it contains something like 175 kilograms of liquid xenon. That's 80% isotopically enriched for xenon 136. So this being a TPC then has this power that you have background rejection from single-site and multi-site events. So if you have a gamma that scatters a couple of times, say in the liquid xenon, it will produce energy deposit that then you can detect occurred once you drift a charge to the anode plane that occurred at 2 separate places. And so you know that can't be a double beta decay, because a double beta decay would occur so at one place. But you do have backgrounds from gammas where they scatter multiply, but those 2 energy deposits are very close together. So gammas can look like single-site events too. And so here's an example of a calibration where in EXO you put a source nearby, and then the source is shooting gamma rays inside, and then you get a spectrum from that source. And these are making, without any cuts, they're making these multiple energy deposits. But you can make a cut selecting the single site only events, or events in which the gamma seems to interact only once, or deposit energy in a cluster that is hard to resolve as being multiple, and then you see considerable rejection of these backgrounds. This peak, which definitely comes from 2.6 MeV gamma that scatters multiple times, gets reduced tremendously, and then other little peaks and so on provide a very powerful background rejection, so that's very useful for the double beta decay. And then XO200 is currently in phase 2 of their operations, in which they presented that they're using not just the sort of position of these deposits, but also the size of the individual clusters of the energy deposit, which they can get from the longitudinal direction pulse rise time, or from the number of wires where the charge is collected. This is illustrated here, that if you have this gamma interacting, we're making 2 charge clusters, and they're pretty close together, so they could look like a single site event. You might have some ability to see that this charge collected on 2 wires, as opposed to a real single site event. So that's information that they included to further improve their background rejection techniques. And so the results are the phase 1 here and phase 2. So this is the 2 neutrino double beta decay that EXO measured. And then the search is at 2.48, I think, 2.48 MeV. The search would be for a peak, which would be the neutrinoless double beta decay peak. And so in the phase 1 data, here are the actual data points now on a linear scale, so you can see just a few counts here. And there is some counts here, and if you were to fit a peak, I think you get a positive value for the fit for the peak. So in this case, unlike the core case, the backgrounds fluctuated up, and that's not there in the phase 2 data. I think that's correct, right, to say that, Andrea? So then phase 2 data, although it's only a short period of time, so you can see the error bars are small, but there's no sort of excess accounts, and then the combined phase 1, phase 2 gives that there's no statistically significant excess around this peak region, which means then you can set a limit for the occurrence of the neutrinoless double beta decay. And so the presentation from the TAP conference was this, that the total exposure of phase 1 plus phase 2 for XO200, then each of the individual phases sets this limit for the half-life for the neutrinoless double beta. It has to be longer than these values, and combined is something like this. So then this half-life limit can be translated into a neutrino mass, this Majorana effective neutrino mass upper limit at the 90% confidence level. So the future for liquid xenon TPC, the EXO project calls this NEXO, and this illustration is of a 5 tons of enriched xenon 136 installed in a TPC, very similar to what EXO200 is like, but then this whole thing would be inside a big tank which provides a shielding, and this is pictured in the SNOLAB cryo pit. So at SNOLAB we're hoping that the EXO experiment will come with their next generation detector, and then could be installed in this space that could be available for that experiment. And inside this would be a TPC with liquid xenon, 5 tons of it, with charge readout now. Charge readout is conventional charge readout, is it, Andrea, or?
No, it's a pad now.
Pad.
Yeah.
Okay. And then the light readout will be silicon PMs instead of APDs, and then silicon PMs lining the barrel too. So aiming to increase the light collection and improve the energy resolution, further improve the energy resolution. So that experiment with 5 tons of enriched xenon would be able to push sensitivity really far for searching for neutrinoless double beta decay. Let me quickly talk about what you can do with a TPC, if you put a high-pressure gas xenon in it instead of liquid xenon. Okay, so the experiment effort is called NEXT, the collaboration. They're trying to build and operate. They have assembled most of the equipment, but I don't think they've operated yet. 100 kilograms of enriched xenon, which they'll operate as a high-pressure TPC. So with high-pressure gas, I mean, with a gas, you don't have, it's not as dense as a liquid, so to get the mass that you want, you need a larger detector. So that's the trade-off. On the other hand, with the gas, the density within the TPC is such that the tracks are longer. And so with this high-pressure gas approach, and they use this electroluminescent readout where you have energy resolution from measuring the light as well as measuring the charge. They aim to have the tracks being part of the identification of the double beta decay signal. So that looks a little bit like this. This is, I think, data from a prototype from NEXT, a very early prototype at that. So the way that works is similar to how I described the TPC in general. You have a plane here where you drift the charge. So here's a track that's produced in the detector, here's a track, and then it produces ionization that then drifts, is collected on a tracking plane. And here they use the electroluminescence produced from the high field region that produces light that then measures the position of the charge that was drifted, but uses light to measure that. It uses SIPMs, the silicon PMs, which are pixelated, so you can get a measurement of the track by measuring the electroluminescent light, at the same time as you can use ordinary PMDs just to measure the scintillation light produced. And again, combining the scintillation and the charge information from xenon, you might get a very good measurement of the energy. And so here, this is shows cesium-137 source. It makes it's a 660 keV gamma, and it makes a Compton electron. And this electron now travels quite a distance here, and you can even see you can measure the DEDX of that electron track. So it has a DEDX, the energy loss per millimeter, and then at the end there's the Bragg peak, the charge blob, we sometimes call it. So then at the very end, the electron loses lots of energy and the density here is high. So you have that ability to measure these sorts of things. It's quite impressive. All right, so I covered these two approaches, and I won't talk about SuperNEMO. If you have any questions about SuperNEMO, an experiment which uses a foil for the double beta source and then becomes essentially a large particle physics tracking detector, then feel free to ask me about SuperNEMO. But I'll jump now to, in the remaining time, talk about this approach where we try to put the double beta decay isotope inside a liquid scintillator and then search for the double beta decay, neutrinoless double beta decay that way. There's a little bit of a history about double beta decay in liquid scintillator. This was the paper from 93, 94 from Raju Raghavan, where Raju proposed that in a large liquid scintillator detector, and it even describes this as being inside the Kamiokande facility. Even if Raju was a key person that started the efforts for Borexino, his paper was suggesting that in any large liquid scintillator, you can put xenon, dissolved xenon gas into the liquid scintillator. And then xenon-136 would be a double beta decaying isotope, and then you would try to search for the neutrinoless double beta decay by looking for events at the end point of the xenon-136 producing scintillation inside the liquid scintillator. So this idea from Raju was studied by Borexino in the mid-90s. It wasn't an actual experiment because we didn't have any. I was part of Borexino back then. We didn't have any enriched xenon. but there were Monte Carlo studies about this idea from Raju. But the actual original plans for CAMLAND, so right from the very beginning when CAMLAND is the liquid scintillator experiment that now has existed for a long time, that used the space of the old Kamiokande water Cherenkov detector. And the original idea when Cameron was proposed, well, let's take that detector and transform it into a liquid scintillator detector, included this notion after this suggestion from Raju Raghavan that we put xenon into the liquid scintillator, and so that was even part of the early days of CamLand. Xenon in liquid scintillator. So a bit of a history for SNO+. Then SNO+ was proposed in around 2003 or thereabouts, when we were looking at ideas, what would we do with snow when we're finished with the solar neutrino program with heavy water and snow. And the xenon idea was out there since Raju Raghavan. And what I was interested in was, let's think about, like we could put xenon in liquid scintillator if we put liquid scintillator in snow. But let's see what other isotopes we could put into a liquid scintillator, just for fun. And so we studied things like perhaps using nanoparticles dispersed inside a liquid scintillator. And so we studied these ones because each of these have possible double beta decaying isotopes. Cadmium is yes, selenium yes, tellurium yes, neodymium yes, zirconium even too. So we tried to make these nanoparticle dispersions in liquid scintillator in my lab, and we had some success with those. And we also looked at making organometallic compounds where you can dissolve things like neodymium or tellurium into a liquid scintillator. And neodymium dissolved as a carboxylate, the same way that gadolinium loaded scintillator is made, was made at Queens and at Brookhaven. And we even made these water miscible mixtures where you take tellurium or neodymium, dissolve in water, and then mix that with a liquid scintillator using surfactants to mix it in. And people like Jin Dai and Alex Wright, used to be my student, now faculty at Queens, did these sorts of measurements. And so we came up with this idea that we could put other isotopes than xenon. Xenon is a very good choice. Maybe we should use xenon. But there are other isotopes, and so it could be interesting to see what you could do. And so then CamLand Zen, of course, CamLand was built. It was built, and so they turned the Kamiokande water detector into a CamLand, and then it was a key measurement of the reactor neutrinos that established the LMA solution for neutrino oscillations, responsible for the solar neutrino deficit as well. And then CamLand proposed in 2009 that they wanted to get some enriched xenon, so then they could put it in based on this, very old idea from Raju. And they would put the liquid xenon in the liquid scintillator. Sorry, they put xenon in the liquid scintillator and put that inside a mini balloon that they would suspend in the middle of the liquid scintillator detector. And so they proposed in 2009, and they had results already in 2012. So in 3 years, they could turn around this wonderful idea and produce these results. So I'll talk about both CamLand Zen and SNO+ in my remaining time. So there's just a little bit of history for where those projects went. Oh, I have one more slide that's history, which is, so currently SNO+, we're aiming to deploy tellurium in the experiment. SNO+ originally was going to use neodymium dissolved in the liquid scintillator to search for double beta decay in neodymium. And the reasons were, back then, was that neodymium does have some advantages for neutrinoless double beta decay. It has the highest phase space. And so then the calculation for how much neodymium you need to have a certain sensitivity suggests that you would need the smallest amount of neodymium. There's some uncertainty in the nuclear matrix elements, as I discussed in my first lecture, but notwithstanding, it is the case that given some calculation, neodymium is the fastest one. And there was the possibility at that time, we learned in 2006, that there was an Avalis facility that produces that can do isotope enrichment for neodymium. A laser isotope enrichment facility in France that existed. This possibility fell through after some few years of study, and officially was dead in around 2011. That there's not going to be any possibility to enrich neodymium. Neodymium, the natural isotopic abundance is 5% for the neodymium 150. So then in around 2011, then SNO+ started to think maybe we don't want to use neodymium if we can enrich it. And there's no other approach that allows you to enrich neodymium because there's no gas compounds you can make out of neodymium. So you need this very fancy and exotic approach with the lasers to separate isotopically enriched neodymium. So Then we looked at ways to make tellurium into a liquid scintillator. So using the very conventional methods that people use for gadolinium liquid scintillator or for neodymium, making this carboxylate, you get all of these different colors that look terrible for a liquid scintillator. So they're so dark, and that means no scintillation light comes from these liquids. But then Brookhaven developed a surfactant approach where you first dissolve the tellurium in water and then you mix this aqueous into the liquid scintillator using a surfactant. And then you could get a sample that looks like this, so very clear. And we're not actually using that approach anymore. In 2015, we developed an organometallic way to load tellurium into a liquid scintillator, and you can get something that then looks like this. Again, very clear. This thing has 19% tellurium by weight in the LAB scintillator. So it's very high loading is possible using this organometallic. And then you do away with any of the issues related with the surfactant in the water. So an approach that gives more light output and higher purity. So we switched to this approach with the organometallic tellurium compound. So then some of the advantages of tellurium for double beta decay, and this is especially important for this loaded liquid scintillator approach for neutrinoless double beta decay at the ton scale, is you'll recall this is the zero nu peak that we're trying to search for on top of this 2 neutrino background. And for a liquid scintillator, it really looks like this. Right? For germanium and a bolometer, it looks like a peak. Right? But for us, our energy resolution is poor compared to that. So then there's going to be this tail from the 2 neutrino double beta decay that comes here, and then we're looking for this peak kind of sticking out at the end of that tail. So it's then very important that tellurium and xenon are the double beta isotopes that have the slowest amount of 2 neutrino double beta decay. For whatever reason, nuclear physics, it has the smallest 2 neutrino to 0 neutrino. Both of those isotopes are the smallest. The fact that we had this initial hope to enrich neodymium and that it didn't work, we were very happy that you don't have to enrich the tellurium. Or you can just buy the tellurium, and then you have 34% of that is the tellurium-130. So that gives that's our approach is try to deploy a large quantity of isotopes. So then you want to have that ability amplified. So we want the small 2 nu background, and then at the endpoint for tellurium, 2.53 MeV, the region of interest for the neutrinoless double beta decay, there are other background rejection techniques that reject the sort of typical backgrounds in uranium thorium that people know about in our low background field with really high efficiency. This famous BIPO coincidence, bismuth-214. Bismuth-214 produces a lot of events in this energy range, but we can reject those with factors like 5,000. Just by looking at this very simple BIPO coincidence. If you see a polonium-214 alpha after this decay, those events are all rejected. So those are all the advantages that are in fact mirrored by the Kamlan-Zen approach. So xenon has the following advantages when you deploy xenon liquid scintillator, is that xenon, just like tellurium, is the slowest 2 neutrino double beta decay, so that's very important. Xenon is likely the easiest and cheapest isotope to enrich, so then therefore Kamlan-Zen could afford to acquire 800 kilograms of enriched xenon. And in their region of interest, which is very close to ours, 2.48, ours is 2.53, it's the same argument. You can also use these background rejection techniques. So this liquid scintillator that have tellurium or xenon, maybe it's very natural that those are the experiments that are going forward with the liquid scintillator approach. I'm going to further talk about the liquid scintillator approach in the context of this study. In the US, they were studying the different ways to select which experiments should be going forward for the next generation double beta decay experiment. This NSAC had a town meeting, and then they had a committee that studied lots of the different experiments that are proposing to take data in the near future. From that meeting, there was this slide, so I'm going to show that slide just to prove that it exists, and then I excerpted all of these points here from that slide. But we've already talked about this maybe in my first lecture. What are the ideal things that an experiment should be able to do in this next generation in particular is what that slide suggests. So you have to have very low backgrounds. You have to have good energy resolution. They proposed in this US study that a scalable approach is important and acceptable costs. Tracking of the betas to identify the double beta event topology is considered very desirable, ideal. large Q value, so your region of interest, you have larger phase space and your region of interest is above backgrounds is also important. That's what SNO plus neodymium was about originally. But then we switched, but we have the background rejection capabilities in the liquid scintillator. So it makes deuterium quite a good choice. And then finally, the ability to remove or replace isotope helps you demonstrate a possible signal by taking isotope out, putting it back in, changing the quantity, and if it's truly a signal that you're seeing, it should scale with the quantity of isotope you put in. So the low to liquid scintillator approach is good at these three, and maybe not so good in these other ones, compared to the other experiments. So let me quickly talk about CAMLAN Zen, and then I'll flash all these things about where we are with SNO+. So CAMLAN Zen, this is a CAMLAN detector, has a balloon with liquid scintillator, and then photo tubes that look at the scintillation light produced in the liquid scintillator. CAMLAN had a program of reactor antineutrinos and geoneutrinos and other things, but by deploying a mini balloon, and then putting the xenon loaded, dissolving, say 3% xenon, up to 3% xenon into the liquid scintillator in this balloon, now you have enriched xenon decaying here, and then they search for neutrinoless double beta decay of xenon. They first put in approximately 400 kilograms of 90% enriched xenon 136 inside this small balloon, and they searched, and CAMLAN Zen has up to 800 kilograms that they want to deploy. So a mini balloon is this, and you have to make a very low background. So here you see pictures that look similar to what Andrea was showing for Borexino's balloon. You have to make a very low background balloon, and you have to take care, so that this is a very common theme in the experiments, is the care you have to take for the background control. And so then they make this balloon and then deployed it, and inside here you have plumbing to allow you to fill it with the xenon scintillator. CAMLAN's phase 1 result, then they observed an unexpected background. So here is where this blue would be the limit they could set for the neutrinoless double beta decay. But then there's a bunch of counts here towards in the endpoints. Here's what the blue limit is proposed to be based on the shapes here, but they do have a lot of background counts that they were not able to, at that point, when they made this plot, identify what the source is, but they suspected it was from silver 110. But there are other possibilities that were there. They postulated the silver 110 came about from the Fukushima nuclear disaster, spreading contamination that then took place around the time they were manufacturing this mini balloon. And so maybe there was some contaminants that got on the balloon, even though they did it in a clean room. And then that silver 110 then produced events in their detector. It's not confirmed that that's the cause. Another possibility is that the silver 110 is cosmogenically produced. That in transporting their xenon, it was exposed to cosmic rays, and then it might have produced these isotopes. And then it's not clear how the silver 110 would have gotten into the xenon part of the liquid scintillator, but if you calculate the cosmogenic production of silver 110 from xenon 136, you actually get about the right number. So it's not clear where this came from, but there was strong evidence that it was silver, because if you give it enough time, the half-life for the silver 110, I'm not sure it's written here anywhere, it just starts to decay. And then they had a program starting from 2012 to first, let's take the xenon out and purify the xenon, put it back in. They found the silver was still there. Let's take the scintillator out and replace with a new scintillator. Let's make a new balloon. And so they did various steps to see what they could do. But of course, all along this time, while they succeeded to do some purification, not by purifying the xenon, but by purifying the liquid scintillator, the silver 110 also decays. And so by the phase 2 results from 2016 reported, here now in this window, that excess of background events from silver 110 is gone, mostly gone. And so then they set a limit on the neutrinoless double beta decay here that they don't see any excessive events at the end point, and so they can set a limit that a lower limit for the half-life. So then you combine those limits from phase 1, phase 2, and you establish, and this I might have shown in my first lecture, that then the limits now for searching for neutrinoless double beta decay on this plot, which has M beta beta here and the lightest neutrino state, Camelin now starts to come down very close to this region, a parameter space that would be consistent with the inverted hierarchy neutrino mass solution. So the future for Camelin is that they want to deploy 800 kilograms of their enriched liquid xenon in a new mini balloon that they are making, and everything would be cleaner with new liquid scintillator, purifying the xenon, and then with this bigger target running for some years. And they also have future ideas to acquire even more xenon, enriched xenon. So I'm almost, I think I'm maybe at the end of my time, but I'll quickly go through where we're at with SNO+. So, but just to summarize, I talked about these 3 experiments, sorry, there's 4, right, and their results, their recent results, Quarry is here, EXO, Gerda, and Camelin Zen. So how you read this plot is like this. So now this is M beta beta on this axis, and this is the measured half-life. Okay, but we know that the half-life is related to M beta beta by these factors in the nuclear matrix element, in the phase space, and GA, and things like that. And then there are different types of calculations, as I mentioned, for the nuclear matrix element that represent the spread here. So each of the symbols is a different group or a different approach for calculating a matrix element. So when you measure the half-life, it translates to the neutrino mass range as given, and it's a factor of a few, right? Because the nuclear matrix element spread is a factor of a few. It corresponds then, if you measure a half-life limit, or measurement, then it corresponds to neutrino mass here. So then as experiments improve, you go up diagonally and you follow these constant bands here, right? So then if this is tellurium here, if you can improve the half-life limit by doing a tellurium measurement like SNO+, you would be up to here. And then maybe SNO+ phase 2, right? So then EXO, if you have the exposure of Camelin, then with a half-life limit here, then it goes up like that. So then EXO is going up, and with NEXO, you way further, and Camelin also going up like this. And this is germanium here. So then that's how you read this. And so these are the current limits, and I don't show the projected limits, say, from NEXO, but SNO+ phase 1 hopes to be here, and this is the range of that inverted hierarchy. So being able to enter this place here starts to give you some sensitivity to interesting. That's right.
For GA, that could...
GA could change the whole, shifts everything. That's right.
Something that is important, right?
That's right, yeah. Okay, so then I'll just take a few minutes to show you what SNO+ is like then. So SNO+ is the follow-up to the Sudbury Neutrino Observatory. So that's SNO, and SNO had 1,000 tons of heavy water. So instead of the heavy water, we keep everything in there, but we replace it with 780 tons of liquid scintillator. So that's SNO+. So because the heavy water was heavier, we used to hold up we still do, we hold up the acrylic vessel with these ropes. But now, when you put liquid scintillator in, but you still have water outside, the whole thing is buoyant with 140 tons of force. The whole thing wants to float with 140 tons. So then we have to put in a low radioactivity net that goes on top of the acrylic and then is anchored to the floor to hold this buoyancy. And then we have to change the logo, and then that's all you have to do, right? You have a new experiment. But then there's tons and tons of things you have to do. So the liquid scintillator, I'll have to go very fast here, I apologize because I don't want to take too much more of your time. But liquid scintillator gives you more light, so then that enables you to search for physics, program, like Borg-Xeno, with solar neutrinos and geoneutrinos, reactor neutrinos, and so on. But then when you put the isotope inside, you also have a neutrinoless double beta decay search. Double beta decay in a liquid scintillator is really searching for this distortion of the spectrum at the end point. The zero neutrino peak is here, and just as that figure that I keep showing, here's the 2 neutrino background really takes off because it's going to be a much larger rate, even if it's a very rare process, than the zero neutrino. So you try to look for this distortion here. Energy resolution of the liquid scintillator is poor, but if you have enough events and the backgrounds are low, then that's what you look for. And tellurium I already talked about. So this is how we make the tellurium liquid scintillator. Our tellurium comes in this form. It's telluric acid. It's TeOH6. And then we react it with this thing called butane diol. And 3 of these, and then these OHs, they combine and off comes water. So this is called a condensation reaction. So you mix these and you heat it, and then the water comes off, and then these stick like this. And now you have the carbon chains sticky on the outside surrounding the tellurium, this thing now can dissolve in the organic liquid. And actually it makes this, or it makes these sorts of structures. And this is a new compound. We looked up what is this thing that we made. They didn't know what it was. So we have a new number and a new name at the Chemical American Society. So we created this thing. And this thing dissolves now in the liquid scintillator. So the key thing though is that you have to purify everything to keep the backgrounds low. So how do you know that, so Borexino has techniques for purifying the liquid scintillator. We learn a lot from Borexino, but how do we purify the tellurium to make sure it reaches the low backgrounds you need? So we have developed these approaches for purifying the tellurium. I have too many words on this slide, so apologies. So, and this one you can't see very well either, but here's an example of what we do. If you take the tellurium and we put in so much cobalt that this looks black, then when we purify it, oh, you can't tell, this also looks black too. When you purify it, this looks like a pink color, and you purify it a second time and it's clear. So you've taken all the cobalt out. So what happens is we recrystallize the tellurium by using nitric acid. So that nitric acid forces the crystals to fall out, but the nitric acid still dissolves all the other impurities, and we wash it away, and then we dissolve those crystals again with water, and then we recrystallize them again. So we're doing recrystallization as a purification for the tellurium. That's a very, that's well-known technique for purifying materials is crystallization. So our signals and backgrounds look like this, a projected signal. So this would be the 2 neutrino background, and here the endpoint is what would be a signal if the neutrino mass was 100 milli-electron volts. So this is the kind of thing we'd be searching for the neutrinoless double beta K, the excess at the endpoint. Whether we do have a finite number of backgrounds, and then our background estimate is here, but the interesting thing is that if we achieve our background targets, and so plus the dominant background is boron-8 solar neutrinos. So the solar neutrinos that was the original signal in SNO becomes the main background for SNO plus if everything else is achieved at as low as we can. So I think that's it. Let me just jump to a summary slide here. We've done a lot with the detector, and let me just show you here. I have some other slides about SNO plus, but in the interest of time, I'll jump to the summary. Is that we've installed this rope hold down, and we've installed the purification systems for the liquid scintillator to be able to purify the scintillator, and we're preparing to fill this acrylic vessel with scintillator, but currently the whole thing is filled with water. This photo shows with underwater cameras showing the acrylic vessel, and then these ropes are here. So SNO plus, we refurbished some of the electronics and upgraded the DAQ. We built some new subsystems, and currently it's filled with water and taking data with a scintillator plant practicing the purification of our linear alkylbenzene scintillator, soon about to start. And then in this photo, I wanted to highlight one thing here from this camera. This little spot here that you see in the photo is a calibration source. So it's taken, we deployed what we call the laser ball. So at the end of this, there's a ball here that then emits light uniformly, and so this was deployed inside to shine light and then measure the optical response of the detector. So we're doing calibrations now, running the detector in water, and we are currently even detecting neutrinos. We see an atmospheric neutrino event here, and here's a calibration source, collimated laser beam installed in the detector, shooting light across the detector. So for the first time, after 10 years that the original SNO experiment stopped, there's the detector's running again, and so then the eventual outlook is that by next year we hope to fill the acrylic vessel with scintillator, and meanwhile we're installing the tellurium systems underground, and those will be operational by the end of, there'll still be one more year of work on the tellurium systems. Those should be operational by end of next year, so we can purify that tellurium using the sort of chemistry that I was telling you about, so that the start of the double beta decay phase for SNO plus will be in 2019. All right, so thanks very much for your attention, and let me know if you have any questions.
Okay, so thank you. We have some time for questions. Who is the first one?
So in your cartoon in the beginning, you had this line shape actually like a bright Wigner. So that motivates my question, is there any hope to actually resolve the natural line shape of the decay? And if you could do so, what can you learn from it?
And you're talking about the neutrinos double beta decay.
Yes.
Right. So I think that the line shape is very well understood because it's just
The shape, yes, but I mean the width.
the width is essentially is then all set by the energy resolution of the detector. Yeah, so that's right. So then those are often sketched as a Gaussian, but detector non-Gaussian features will show up, but it's all detector related. But the actual shape is well understood from the kinematics of the nuclear decay.
So no hope to ever go there to have the resolution so well that you could find the natural width.
Right. I think there's no even those experiments that have the outstanding energy resolution in the end the shape, the natural shape is still line right compared to those widths.
Have you considered cleaning the acrylic like Deep did with a scraper and a robot?
Right. So in the original plans for Snow Plus, we were going to sand the inside surface of the acrylic. Now, Deep had this robot that would do it all automatically, but the Deep acrylic vessel is much smaller compared to this. So we were going to send people inside and put on, it was still going to be robotic, but it would be putting on a frame, and then the robot would sand this area, and then you have to move it. So this was tested and developed, including things like sanding some acrylic where you spike it with lead-210 and seeing how much comes off and these things like that. But you have to remove the lead. If you want to make a big difference, you want to remove it like by a factor of 100 or 1,000. And that means actually the bigger challenge is you can't miss a tiny portion of it as you're doing this pattern around, and you can't miss 1/1000th of it, of the area. And then there were some problems with the planning for deploying the people inside and how you access it and the actual function of this, that we realized that the risk that you introduce contamination by putting people in this long campaign to sand is probably higher than the gain you get by sanding off the lead-210 that we think is there. The lead-210 eventually could impact the CNO measurement for us in Snow Plus. So we're sad that if that turns out to be the case, but the plans then are we're operating currently filled with water. This is leaching some of the lead backgrounds off. And then later, when we fill with scintillator, then the leaching of lead and bismuth-210 becomes much, much smaller than when it's in water. So then that's the initial plan. We'll see how low that is. And if it's very low, then we may be able to do the CNO neutrinos. If it's not, they'll have to wait. And so then, because there's a push to do the double beta decay, we do the double beta decay measurement. Then we don't know which way that's going to go. If, let's say you discover double beta decay or something, we don't know which way. But if at the end, if you remove the tellurium, which we can do with our scintillator purification system, we're also possibly removing the lead or other backgrounds. We'd have to remove, it'd be a big campaign for purification, but in principle you could remove all of the tellurium and then all the other backgrounds and then try to run for the CNO solar neutrinos if it turns out that that's a background. Right. That's many years off.
There is another.
Okay. I have a more general question, and is how will be affected the current neutrino double beta technology, the fact of having either tellurium or xenon double beta isotopes in the form of solid state detectors. I mean, instead of having only scintillator signals, also having phonons, right?
Yes. And so to make these phonon type detectors, a bolometer with the tellurium is the Corey experiment. There are other ideas too about what you could do with tellurium, possibly even a tellurium semiconductor. There are semiconductor materials that are, CZT, this cadmium zinc telluride, and then tellurium exists in there, and there's also an experimental effort that existed for a time called COBRA, where they were trying to look at CZT semiconductor detectors which have energy resolution similar to germanium, and then tellurium is there. On the other hand, the technology is not the same level as making a germanium detector, so those were very small crystals they're making. It has, but it's potentially interesting to think about what you can do as a solid-state detector for tellurium. Those efforts like EXO or in the liquid scintillator, having the liquid detector has some advantages. Even if we don't have the energy resolution, you can repurify the liquid even in situ. So once you make a crystal, then that's it, right? So if it's not clean, that crystal, you have to remake a new one, right? But in the liquid, if there's some contamination, you have a hope to potentially lower it. Cameron then has done that, right? Because they actually accidentally had contamination in their liquid xenon scintillator, and then they have reduced it. Some of that may just be the decay of the silver 110, but there's some hope that you can do that. So there is some advantages with the liquid detectors, so. But it's a good suggestion you have to always think about what you can do about solid-state detectors or other detector technology.
Thank you.
No more questions? So if not, let's thanks again to all the speakers. And we finish the morning session. We see everybody here at 4 again. There is a book that was